thing. There we go. So in her presentation yesterday, Hong talked about the need for interesting Riemann solvers on these PDEs on networks. She's been working with Aidan Hamilton from the University of Delaware, and he's going to tell us about that. Thanks for being here with us, Aidan.
Yes, thank you. So I'm Aidan Hamilton. I'm a graduate student at the University of Delaware. This is a work in collaboration with my advisor, Jing-Mei and then Ms. Hong Zhang with the PETSc team. And I'll be presenting Riemann solvers for hyperbolic networks. So my talk is just going to basically introduce what are hyperbolic networks. I assume that most people are not familiar with them. And then I'm just going to go in sort of the background details of what those things are, and just discuss the implementation, how do we actually solve these things, how do we make them scalable, then some numerical results. So hyperbolic networks are just adding a hyperbolic conservation law onto just a network. So you have a graph, you add some geometry to it, you put a 1D PDE on there, and you have a system of conservation laws that naturally extends just edgewise to the network. The only problem is trying to couple these things together, and that is where we're going to get into doing Riemann problems. I'm also only ever going to consider small systems, scalar equations, and 2x2 systems, because trying to extend beyond that for these types of models is very much an open problem, just at the modeling level. So there's two different PDEs that I would consider as the main examples, and they both deal with kind of different areas of this type of problems. So just shallow water equations, simple, nice. It's the sort of quintessential 2x2 system for these types of problems. And you just are solving just a conservation law for water height and then water momentum. And then we also have a traffic flow problem, which is the scalar problem, just LWR model. Fairly simple. This is a macroscopic model for the density of cars and traffic simulations. And the shallow water equation is sort of the case of you have a 2D, really you have a 2D, 3D problem in real world, but you really only care about one dimension of it. So very large river network, for the most part you can, if you're looking at a high enough scale, you don't really care about all the local 2D behavior. You can kind of model that away, get a bunch of 1D problems out, and just couple them together. And if you solve it that way, it is so much faster for you. The traffic flow case is different in that the network is the model. There is no really other way to do these macroscopic traffic simulations. If you want to handle simulating the traffic in Chicago, you kind of have to go to the network case if you want to go beyond anything other than just like a straight road. And just small notes, the PDEs. For the shallow water case and just 2x2 systems in general, you really, really care about fluvial or fluvial-like conditions, and we'll see that as we go to the Riemann solvers. You need to have eigenvalues with different signs to make this work in a simple way. Again, people are trying to extend that to other cases, but it is an open problem. It becomes somewhat challenging. So for those who aren't familiar, just 1D Riemann problem, just solving these 1D conservation laws with a jump condition and trying to solve those things, which gets into just solving rarefaction waves, shock waves, coupling, and being able to connect these things together in phase space and going through all of that. And in 2x2 systems, you'll end up with a solution that looks like that. You'll have a left state, right state in the center. You'll have the star state, which is what we're going to end up caring about trying to solve for. And the star state, as I said, is just found by finding an intersection of two nonlinear curves in phase space, which are just given by looking at your PDE and figuring out what are rarefaction waves, what are shock waves, how do you connect them together. And for the shallow water, this would just be an example of what it would end up looking like. The Riemann problem of the vertex is it's an extension of these Riemann problems, just 1D Riemann problems, to the case of you have multiple 1D problems all connected at a single point. So for every single edge at a vertex, you have a single constant state, and you need to somehow connect these together in a sensible way that respects the physics, can handle rarefactions, can handle shocks, and will be stable. So in this case, you do need an extra degree of the vertex coupling conditions to make this thing well posed. The physics alone is not enough. You need additional modeling assumptions. For shallow water equations, these are just adding other, in this case, linear equations to the system that makes sense. You can choose other things. People do. Depends on the situation. But this is a fairly common choice where you just assume height continuity, and then you always consider a conservation of mass. There's no reason not to. So the fundamental principle of solving this is you want to connect each Riemann state to a star state by a single wave curve so that information travels out of the vertex. That means you always are coupling things by physically relevant waves. In this way, you can always handle shocks, rarefactions, everything, and it'll work. However, this is where you need to have that fluvial conditions to make this thing work. If you have non-fluvial, you cannot make this assumption. And there are papers where people try to not make this assumption, and those get very, very long, very, very quickly about trying to handle like vacuum states. And I'm going to ignore that because it's difficult. Now for the LDOBR case, you end up with actually an optimization problem on every vertex. So what you do is you assume in the modeling level you get some traffic distribution matrix, which is just handed to you by some modeler who knows what they're doing, and dictates how at a road, how should traffic move from outgoing roads, one-way roads, to another road. And if you're given, you can always have this point that these flux functions, because we're assuming strictly concave for them. You can find a point that it attains its max. You define these two little functions here, which are really just handling that question of making sure that you have a wave that moves out of a vertex. In the scalar case, you can kind of just embed it. You don't have to solve an extra equation for it. And you end up with in this case, just a linear programming problem. I don't solve it properly. I want to be using PETSc because I'm using PETSc for everything I'm doing, and I like the PETSc interface, so I am doing the wrong way of solving it, which is going to be using tau ALLM. However, it doesn't end up mattering that much because these are fairly small. So now we go into, I kind of know how I'm going to couple things together in a physically relevant way. Now I'm just going to discretize this thing. So we just use a standard RKDG framework. It's 1D problems. We've known how to do this for a long, long time. So just evolve a discontinuous polynomial, numerical fluxes, and doing the Riemann problem is, the only problem is getting those fluxes on boundaries. That's why we were solving those Riemann, or cared about those vertex Riemann problems in the first place. That's what will give us that magic to couple everything together. We solve in time just by strong stability preserving RK methods, TSSP and PETSc, and we use a total variation bounded slope limiters for stability, and that uses TS post stage to just modify the solution to make sure that we don't have oscillations that blow our solution up. And we have to then solve these network Riemann problems at vertices to get these boundary fluxes. And that's where all the really difficulty comes into play. So I want to do this at scale. I want to do this in parallel. I want to do this without wasting a ton of time. And because there is a variety of things that these vertex Riemann problems can be, they can be tau, they can be SNES, they could be KSP type things. I just end up writing my own classes to try and abstract away all that, because the interfaces are very well defined. It's just the actual implementations that would change problem to problem quite a bit. So just in a branch of PETSc, that is somewhat ugly code, but it seems to work, I just added two Nexter classes that just sort of wrap these problems for me. So network Riemann problem that specifies and abstracts away all of those varying cases I could have for my model problems. And then something on the top that's just going to solve all these and handle parallelism, can handle essentially a poor man's batching is what I'm going to be doing. And handle the fact that for DMNetwork, at least currently, there is no real notion of ghost edges. So I have to work around that. Ideally, I would like to make it so DMNetwork can handle that on its own, but that was a little bit more work to do that, so I just kind of danced around it a little bit and built this network Riemann solver to try and hide that sort of difficulty in implementation. So as I said, every vertex Riemann problem requires some sort of PETSc solver. I'm going to be either using it in SNES and shallow water occasions to solve a bunch of small little nonlinear problems. Or in the traffic case, I'm going to use the tau to solve it in the wrong way, but it'll solve it. For all these problems, though, the problem structures only end up depending on vertex degree. So every problem that I'm going to be solving on every vertex has the exact same structure for it. So I can reuse that. I don't have to have a separate solver and a separate solver objects for every single vertex on my network. These are going to be fairly large networks. For one of the larger ones I solve, it's nearly 1 million vertices. I don't want to have 1 million tau objects. I don't want to have 1 million SNES objects floating around. So this network Riemann problem just caches them. So I only maintain a single solver and objects around to support that solver for every vertex degree. For the shallow water case, you end up having a map from vertex degree to SNES. In the traffic case, those depend on the in degree and the out degree, so then I have to cache based on that pair. But it all ends up working the same way. And then that way I can also, because these are small problems, I can just reuse a symbolic solvent during the just when I solve this direct LU factorization. And you do see significant speedups from doing that, because then the solves become extremely, extremely cheap. And so net Riemann solver, how that thing gets used. So I'm using a DM network to manage these network topologies in parallel. So given a DM network, this thing will just take it in, create a clone copy, and then just take control of it and do what it wants with it. I can assign network Riemann problem objects to the vertices of DM networks. This lets me collect a bunch of different network Riemann problems together. Potentially, these could be different network Riemann problems, particularly that's how I implement boundary conditions. I have different network Riemann problems for doing boundary conditions at degree 1 vertices. And the network Riemann solver will then generate a PETSc section and a corresponding global vec to be able to store and handle all of these Riemann problems at once. Hence, I'm going to be doing poor man's batching. And then, when I actually want to solve, I just set the local Riemann data into this big global vec. I have to handle indexing myself a little bit because of the lack of ghost edges for DM network. So I have to do a little bit of work myself, extract an SF, and be able to compute some indexing to make this all work, but it gets done on the back end. And then I can then solve all the Riemann problems, just all at once. Just I will call like a network Riemann solver solve. And it'll try to do some basic interlacing, trying to solve all the local problems when it can, while it waits for communication for non-local data. I also have an optional solve begin, solve end type interface, which I do use when I'm doing DG, so that I can interlace with doing all the DG updates. And in that way, you don't really see any communication overhead in practice. And so what the algorithm ends up looking like is just iterate through all the vertices in the network, evaluate your DG solution at vertex points, collect that forms your Riemann data for the global thing, then just do a solve begin. It'll solve some things where it can, it'll communicate what it needs to, and then while that's going on, then I'll just update all the DG where I can, except for the boundary fluxes, and then after that I can just solve end and then finish up with the boundary fluxes. And in this way you tend to see fairly good scalability, and you don't really see too much degradation with the communication, as long as you of course have enough work. So I'm from the math community, so I'm just going to show at least that this thing converges. This is just a smooth problem solved up to, or it's smooth to a certain time. I solve it up to the time where it remains smooth. It does have this is a problem that has a non-trivial interaction at vertices. So it's not, it is truly a network level problem, but we can see we can get the orders of convergence we would expect. So at least it's not going completely wrong. And I will have a case that shows a dam break on a shallow water network. I just have that in a movie that I will show kind of at the end, just to show that we at least can handle a shock condition in a sensible way. Similarly, just a basic traffic network example that shows at least things seem to be working. A movie at the end. And one of the major sort of scalability cases we did is we wanted to simulate the entire Mississippi River network all at once. And so we obtained the data from an HD Plus data set. Contains about 900,000 edges, about similar amount of vertices. We discretize with a length scale of 10 meters, which is a little ridiculous, but we just wanted to push it and see what we could do. And that's the full resolution of the data set, P2 basis, 5-stage SSP RK2 method, and we end up with about 1 billion degrees of freedom. We did the simulation on theta, and just did a strong scaling test for number of cores, just for the time step. And just see, can we get a single time step to strong scale reasonably well? In particular, yes, we do get the strong scaling we would like. Particularly the network Riemann solver itself strong scales independently. That's really the only part that does any communication. So it's nice to see that that part itself will actually do strong scale. And so future work, just implement more physics and be able to simulate more physics. I have some collaborators that have been patiently waiting for me to be able to do these things for them. I would like to do more large-scale simulation for traffic flow. Recently built the ability, hacked in a HDF5 reader for DMNetwork that works well enough to be able to load in a workflow where you can grab a traffic network from essentially Google Maps. I can build the DM network out of it, and then I can do physics on it and solve a traffic flow on just real traffic networks. General code improvements. I've been developing all this stuff just in a branch of PETSc, mostly so I can keep PETSc's nice build system and not have to deal with that stuff on myself. I should probably move this out at this point and create a separate area for it to be actually used. And as well in developing this, there are a lot of pieces that really should be moved into PETSc itself, particularly with DMNetwork. There's a lot of code in here for computing sort of topology things, being able to handle certain conditions, doing some visualization that really should be migrated back into PETSc itself. It's just making it a little bit prettier. And those are the references. And then at the end, I'm just going to quickly show just a video of what these things end up looking like. Oh, I didn't mean to stop sharing. One sec. Share screen. So for example, in the shallow water, you consider just a dam break problem that propagates in, say, a grid graph. And you can see the sort of non-trivial interactions you get. On the left-hand side, you have momentum. On the right-hand side, you just have the water height just propagating through. And it's, at least for me, I find it fun. And then similarly, we can do the same thing for traffic, if I can find where I put that. Did it not get uploaded? Okay, well, I can't seem to find the traffic one, but we'll move on. So that just concludes my talk. Thank you.
Thanks, Aidan. Even without the traffic one, it's fun to see these type of solutions being done on networks in comparison to, we all see dam bursts happening on fields or continuous domains. Any other questions? All right. So it's your solution to wrapping a bunch of different solutions, SNES, KSP, and tau, in something. You don't need to shrug. I mean, we all have these sort of higher level problems where an outer loop can go around multiple different types of things, and so it's interesting to see what you worked out in practice, and it may help us figure out what we do going forward for similar problems in the future.
Yes, and particularly, as I said, this is essentially poor man's batching, as hopefully at some point in the next few-ish years and PETSc implements some sort of batching capability. It'd be nice if something like this was able to be included in that, and I don't have to handle it myself as much, and it could be handled in perhaps a more appropriate way than how I do it.
Sure, as Dave said a couple days ago, it's great when you can hand off the burden to other people for your code. All right, let's thank Aidan one more time.